Gee, Mike, what do you want to do tonight?
Same thing we do every night, Reese. Try to take over explain Hazelcast technology to our loyal listeners.
Brilliant plan.
In this segment of our look into Hazelcast's pipeline API, we'll be adding windowed aggregations to our pipeline. Now, usually when we revise our pipeline, we take a look at the code first, and then we see how the DAG reflects the changes we made in the code. But let's flip that around this time and look at the DAG here first. Now, in version 7, as you can see here, we took one leg of our pipeline that was just simply syncing details into an IMAP, and we've hung a couple of additional branches off of here that allow us to do additional processing in parallel with the aggregations that are already in place. Now, the aggregations we added before were rolling aggregations, and those are happening in this branch. And in this version of the pipeline, we're going to add some windowed aggregations, which run for a specific window of time. And we're doing two different time windows, so we've got two different branches here that use different time slicing. Our windowed aggregations are going to allow us to implement a simple mechanism to identify trading opportunities. In trading, it's common to take a moving average of prices to smooth out the inherently spiky nature of the market's movement. One of the market patterns that some traders look for is known as the death cross, which is a negative or sell signal when the short-term, say 50-day moving average of a stock moves below the longer-term, say a 200-day moving average of that same stock. There is also the mirror image of this, which is known as the golden cross, when the 50-day average moves above the 200-day average, and that's a positive or buy signal. Now, in order to demonstrate this without having to wait and generate 200 days worth of trades, I've changed the 50-day and 200-day averages to be 50-second and 200-second averages, and I take no responsibility whatsoever for how poorly this strategy might perform against real-world markets. So to accumulate averages over our periods of 50 seconds and 200 seconds, we're going to use windowed aggregations. Now, as a refresher, in our last episode, we used rolling aggregations as shown here at the top. We specified a grouping key, which is optional, and then followed that with a rolling aggregate stage. For our windowed aggregations, which are shown at the bottom, we can define our grouping key just as before, but we add an additional step where we define the window over which the aggregation will be performed. Then we add our aggregate stage, which is no longer a rolling aggregate, but accepts the same kind of aggregate operations to apply to the data stream. JET supports three types of windows. We'll look at tumbling windows first. We can define a tumbling window using just a single parameter, the window size. The size is time-based and is stated in whatever units match the granularity of our timestamps. Since Kafka timestamps are in milliseconds, here we're declaring a 10-second tumbling window. For simplicity, I'm showing our timestamps as integer values, and let's just pretend that we're conveniently getting new items at the rate of 1 per second. So with a 10-second tumbling window, timestamps 1 through 10 would be collected together for the first window, and then 11 through 20 in the second, and so on. Each item belongs to exactly one window, and the windows do not overlap. Tumbling windows are great if you're doing something like aggregating sales per hour, where the time frames are disjoint. You might want to know sales in the noon hour versus the 1 p.m. hour, but you probably don't need to know sales between 12:07 and 1:07. But this doesn't match the definition of how moving averages should be calculated, so this isn't going to be a fit for our current use case. A sliding window is defined by two parameters. The window size is the range of timestamps that will be included in each window, just as with a tumbling window. The second parameter is a slide by. Sliding windows overlap, and the slide by tells us how far each window is offset from the one that precedes it. The slide by causes our stream of data to be divided up into frames, which become the unit of aggregation. So in the diagram here, each box represents a frame. If we have one item per second, then each frame is just a single item. But if we had 100 items per second, each frame would contain 100 items. And of course, in most items, items won't arrive at a constant rate. So while the timestamp range of a frame is constant, the actual item count will vary. Our first window of 10 seconds will encompass all the items in frames 1 through 10. And then we slide 1 second or 1 frame so that the second window includes frames 2 through 11. The third window covers items or frames 3 through 12, and so on. And this works well for calculating a moving average, so this is the window type we'll add to our pipeline. Fun fact, tumbling windows are really just sliding windows where the slide by length is the same as the window size. Mind blown, right? The last window type is a session window. Unlike the other windows, session windows are not all the same size. The size is defined by the data. A session window is configured with a timeout. What period of inactivity will cause the window to be closed? Session windows are great for tracking web activity where we can process click streams for as long as a user is active, but once they leave the site, we can close the session window and create a new window for them if they come back. IoT use cases like telemetry from a car are another use case. As long as the vehicle is on, we can collect useful telemetry. But once it's parked, we can close off the window representing that trip and begin a new window when new data is received. With any of these three window types, results are passed from the window stage to downstream stages when the window completes. When you have large windows, like the 15 minutes we're showing here, or perhaps several hours in the car trip example, we might not want to wait until the window closes to see partial results. So all three window types allow defining an early results period. And when set, we'll get intermediate results at the requested frequency. Each result will have an isEarly method we can test to know if we're looking at a final result or an early one. Adding windows to our pipelines is pretty simple. The API hides a lot of complexity, and I want to briefly hit on a couple of things that are useful to know when building efficient pipelines. We saw that with tumbling windows, each trade would only belong to a single window, but with the sliding window, it belongs to many overlapping windows. A 50-second window with 10 trades per second arriving means we would accumulate 500 items for each window, with 50 different overlapping windows being active concurrently. That's a lot of aggregating. To make the calculations more efficient, JET doesn't iterate over the entire contents of the window for every aggregation. Instead, as the window slides, we deduct from the aggregation the frame that we just moved beyond and combine into the aggregation the accumulated values from the frame we are advancing into. We talked about windows and timestamps as if all our events arrived reliably at the instant they occurred. In reality, congestion, delays, and other issues can cause events to arrive delayed and even out of order. There are a few settings that we can tweak to accommodate these real-world deviations from our ideal. In many cases, event order isn't significant. All of our pipeline's aggregations are commutative, so we don't worry if items have been reordered. But if it matters, we can call set preserve order true on our pipeline. Ordering will be preserved, but overall throughput will be reduced as the opportunity to parallelize operations will have been reduced. Event lag is another complication we may encounter. In our case, if a trade is delayed and arrives after the window it belongs to is closed, it will be dropped from the aggregation. We can mitigate this by adding an allowed lag parameter where we specify the timestamp strategy for the pipeline source stage. Allowed lag will essentially postpone the closing of the window for the specified grace period, and any events arriving during that period that belong to the closing window can then still be added. Events arriving during the lag period whose timestamp places them in a later window will be added to that window as usual. So there's nothing surprising here since we introduced it all in the slides. We have two blocks of code here that each work against the same set of input items. One has a 50-second window and the other one a 200-second window, and both windows are sliding by 1-second increments. We have a simple aggregation to take the average price of all the trades that happen during the interval. We pass these aggregations into a service that we haven't talked about yet. You have to come back next week for that one. And whatever we get back from the service, we write to our logger. Now, spoiler alert, map stages can also act as filters by returning null. So if our service returns a null, then we're not logging anything. But when we detect one of the patterns we're looking for, a death cross or a golden cross, we're going to return an alert, and that will get logged here. And that's it for windowed aggregations. So what are our takeaways? Are you pondering what I'm pondering? We have three types of windows that we can add to our pipelines: tumbling, sliding, and session windows. These windows can all be used with or without a grouping key. Windows are used when the time aspect is key to analyzing the data. So tune in next time as we look at the pipeline's service invocation methods and how we can use that to add functionality that exists outside of our pipelines into our workflows.